This is the tornado that broke the rules meteorologists thought they understood. On May 27, 1997, an F5 formed in a place where the science said a violent tornado shouldn't have been possible, moved the wrong direction, slowed to a crawl over a single neighborhood, and left behind some of the most extreme destruction ever recorded on the surface of the earth. 27 people died that afternoon, every single one of them in the same small subdivision in a span of about 3 minutes. And in the years since, the Jarrell tornado has become something more than a disaster. It's become a puzzle that forced tornado science to grow up. To understand why, you have to start with what should have happened that day and didn't. Jarrell sits in the flat heart of central Texas, in the northern part of Williamson County, roughly 30 miles up Interstate 35 from Austin. In 1997, it was a quiet farming town of about 1,300 people. It wasn't a stranger to bad weather. 8 years earlier, in 1989, an F3 tornado had already torn through the area. But nothing in the town's history and nothing on the forecast that morning pointed to what was coming. Here's the first strange thing. When forecasters looked at the atmosphere over central Texas on the morning of May 27th, they saw a setup for strong winds and large hail. What they did not see was a setup for violent tornadoes. And that wasn't a mistake. It was based on decades of hard-won understanding. For a long time, the recipe for a monster tornado seemed clear. You need instability, the raw fuel that lets air rise fast and hard. And you need wind shear, which is the change in wind speed and direction as you climb higher into the sky. Shear is what takes a rising thunderstorm and sets it spinning, tilting that spin upright until the whole storm becomes a slow, rotating engine called a supercell. Strong, deep layer shear had always been the fingerprint of the most dangerous days. When the shear was weak, forecasters relaxed. Weak shear meant disorganized storms. It didn't mean this. And on that day, the shear was weak. The winds through the atmosphere weren't changing much with height, which is exactly why the tornado threat looked low. The ingredient that was supposed to be missing was missing. But there was one number that afternoon that should have made everyone nervous. It's called CAPE, convective available potential energy, and it's a measure of just how much fuel the atmosphere is holding. Think of it as the potential violence stored in the air, waiting for a trigger. On May 27th, the CAPE over central Texas was enormous. The air was hot, thick, and soaked with moisture, and it was capped. A warm layer higher up was sitting on it like a lid on a pot, holding everything down. For most of the day, that lid held. And then the afternoon sun did its work. The heating built, and the cap broke. When it did, all that stored energy came out at once. The storms that formed weren't ordinary. And they did something that should have been another warning sign, because they moved the wrong way. Most storms in this part of the world drift toward the northeast, carried along by the upper winds. This cluster of supercells crawled toward the southwest instead, backing against the usual flow. It's a small detail, but it's the kind of detail that tells you the atmosphere isn't behaving normally. Out of that cluster, 20 tornadoes would touch down across central Texas before the day was over. Most were brief. Several were destructive, and one of them, forming just northwest of Jarrell in the early afternoon, would become the strongest tornado the United States had documented in years. At first, it didn't look like much. Eyewitnesses described a thin rope of a funnel, the kind of tornado that often lasts a minute and fades. But this one didn't fade. It fed on that extraordinary fuel, and it grew. Within minutes, the rope had swollen into a churning multi-vortex monster, nearly 3/4 of a mile wide. People who saw it never forgot the shape. It didn't look like the clean cone you picture when you think of a tornado. It was a dark, ragged wall with smaller funnels spinning inside the larger circulation, a mass of vortices braided together. Storm observers gave it a grim nickname that has followed it ever since. They called it the dead man walking, because in silhouette, those churning inner vortices looked like a giant figure striding across the fields toward the town. And then it did the thing that made Jarrell. It slowed down. A typical tornado is a moving target. It races across the landscape at 30, 40, 50 miles an hour, and even a violent one usually passes over any single spot in seconds. That brief contact is often the difference between a damaged home and a destroyed one. Speed, as strange as it sounds, is a kind of mercy. Jarrell had no mercy. As the tornado reached the Double Creek Estate subdivision on the northwestern edge of town, it slowed almost to a stall. For roughly 3 minutes, that 3/4-mile wide core of F5 winds sat grinding over the same few streets. 3 minutes doesn't sound long. Standing in front of the most violent winds on the planet, 3 minutes is an eternity. We don't know exactly how fast those winds were, and that uncertainty matters to this story. In 1997, the mobile Doppler radars that can now measure a tornado's winds directly were brand new, and none of them were anywhere near Jarrell. Nobody clocked this tornado. Everything we know about its strength, we know from what it left behind, and what it left behind is almost impossible to describe. The Fujita scale, the system used at the time to rate tornadoes, tops out at F5. An F5 rating corresponded to estimated wind gusts somewhere between 261 and 318 miles an hour. Jarrell didn't just meet that bar. Survey teams who walked the wreckage said it blew past anything the scale was built to describe. In Double Creek, about 40 homes were leveled, not damaged, not flattened into piles of rubble, leveled and then swept away. The National Weather Service survey noted that many houses were blown completely off their foundations, and the disintegrated remains were carried off, leaving only bare concrete slabs where families had lived that morning. In the worst hit spots, investigators found only small debris. The large pieces, the walls, the roofs, the structural bones of a house were simply gone. The ground itself was attacked. The tornado scoured grass and topsoil down to bare earth. In places, it tore the asphalt off the roads. Vehicles were picked up, thrown, and flattened, and several dozen of them were found scattered across open fields, mangled and packed with mud and grass driven into every gap. Trees didn't just lose their branches, they were stripped of their bark. And in a detail that has haunted this event for decades, cattle grazing in a pasture near the subdivision were killed and carried as far as a 1/4 mile away. This is the part where the numbers stop being numbers. 27 people were killed in Double Creek Estates, and the way the tornado behaved is inseparable from why so many died. Because it moved so slowly, and because it grew so violent so quickly, there was very little time and almost nowhere to go. Central Texas homes rarely have basements. The ground is hard, and for most families, the safest room in the house was still inside the house. Against an ordinary tornado, that's often enough. Against this one, being inside a house on a slab offered almost no protection at all because the houses themselves were being removed from the ground. Whole families were lost. In a town of 1,300, nearly everyone knew someone in that subdivision. The grief didn't stay in Double Creek. It spread through the schools, the churches, the small businesses along the highway, and it never fully left. It would be wrong to tell this story as nothing but horror, though, because that same afternoon, a few miles away, you can see what a difference a decision makes. In Cedar Park, as a separate tornado from the same outbreak bore down, the manager of an Albertsons grocery store had gone out to the parking lot to watch the sky. He saw what was coming. He went back inside, had an announcement made, and gathered the roughly 60 shoppers into the center of the building, away from the windows and the walls. The store was badly damaged. The people inside survived. On a day defined by how little control anyone had, That one clear-headed choice saved dozens of lives. But in Double Creek, there was no time and no shelter that could have held. And when the tornado finally lifted, just 13 minutes after it had formed, it left behind a scene that professional meteorologists, people who study destruction for a living, struggled to put into words. So the question became, how? How did the atmosphere produce this on a day when the tornado threat looked low, from an environment that was supposedly missing the key ingredient? This is where Jarrell stopped being only a tragedy and started being a lesson. Remember the weak shear. By the old rules, weak shear meant the storms shouldn't have been able to organize into long-lived tornado-producing supercells. But Jarrell proved that the old rules were incomplete. What that day revealed is that when you load the atmosphere with enough raw instability, when the cape is high enough, you don't necessarily need strong, deep wind shear spread through the whole atmosphere to make a violent tornado. You can make one with tremendously powerful updrafts interacting with more localized, low-level spin, the kind that collects along boundaries near the ground, like gust fronts and dry lines, and the edges of colliding air masses. In other words, there's more than one recipe. The classic high shear day is one path to a strong tornado. But a high instability, low shear day, the so-called low shear high cape setup, is another, and it's one that older forecasting rules were prone to underestimate. Jarrell became a benchmark case for that entire category. It's now taught as a warning against reading a single ingredient and relaxing. Then there's the slow, backward movement. Those southwest moving storms weren't just a curiosity. That unusual motion, combined with the near stall over Double Creek, is a huge part of why the destruction was so total. And that raised an uncomfortable question about how we rate tornadoes in the first place. Because here's the problem. The Fujita scale rated tornadoes by the damage they caused. But damage isn't only a function of how fast the wind is spinning. It's also a function of how long that wind stays on a target and what the target is built like. A moderately strong tornado that sits on a well-built house for 3 minutes can do more damage than a stronger tornado that passes over in 3 seconds. When you rate purely by the wreckage, you can't fully separate the raw intensity of the wind from the duration of the exposure and the strength of the structures. Jarrell was so extreme that it forced meteorologists to confront exactly how blurry that line had become. And underneath all of it was the measurement problem. Nobody had measured Jarrell's winds directly because the technology to do it safely wasn't there yet. All the scientists had was the aftermath. That gap, the frustrating distance between what a tornado does and what we can actually measure while it's happening, was one of the pressures driving a revolution that was already beginning. Mobile Doppler radar, the truck-mounted units that could be driven toward a storm and could scan a tornado's winds in real time. You know this technology, even if you don't know its name, because it's the same class of instrument that, 16 years later, would capture the extraordinary data on the El Reno tornado that changed how we think about tornado size and structure. The road that leads to those measurements runs straight through cases like Jarrell. Storms so violent and so poorly quantified that the science community knew it needed a better way to see inside them. And the questions Jarrell raised about the rating scale itself didn't go away either. The unease about a damage-only system, a system that couldn't cleanly account for construction quality or the strange physics of a stalled tornado, was part of a broader conversation that eventually produced the Enhanced Fujita scale, adopted in 2007. The new scale tied wind estimates much more carefully to specific types of structures and how they failed. It was an attempt to make the rating fairer and more physical and less dependent on the accident of what a tornado happened to hit. Jarrell wasn't the only reason that conversation happened, but it's one of the cases that made the need for it impossible to ignore. There's one more piece of Jarrell's legacy, and it's a quiet one. In the years since 1997, the United States has seen other violent tornadoes. But as of today, all these years later, Jarrell remains the most recent F5, or EF5, tornado to strike the state of Texas. In a state that sees more tornadoes than almost anywhere on Earth, nothing since has reached that highest rating. That fact alone tells you how rare and how extreme that 13-minute event really was. So what do we take from it? Jarrell is remembered rightly for its human toll. 27 people, one neighborhood, one afternoon. That's the part that matters most, and no amount of science should ever crowd it out. But Jarrell endures in the record for another reason too. It was a tornado that refused to follow the rules. It formed where the guidance said the risk was low. It moved against the flow. It stalled where storms are supposed to race, and it destroyed with an intensity that the tools of the time could describe only by pointing at the wreckage and admitting the scale had run out of room. Every one of those anomalies became a teacher. The weak shear formation reshaped how forecasters weigh instability against shear and made them slower to relax when one ingredient looks missing. The total destruction sharpened the questions that helped push tornado rating toward a more careful, more physical system. And the maddening absence of hard measurements added fuel to the drive for the mobile radars that now let us look inside these storms while they're alive. The atmosphere over central Texas that afternoon didn't break any laws of physics. It just broke the simplified rules we had written down to describe it. And that's the thing about the science of extreme weather. Every rule we make is really a bet, a best guess based on the storms we've seen so far. Now and then a storm comes along that collects on that bet all at once and forces us to write the rules again. Jarrell was one of those storms. It took 27 lives in 3 minutes, and in doing so, it left the rest of us with a hard, permanent lesson about how much we still had to learn. The least we can do is keep learning it.